All right, hello everyone, and welcome back to the video lecture series on confidence intervals. So in the last video, you guys learned that we can use the standard normal distribution to construct a confidence interval to estimate the population mean if the population standard deviation sigma is known. However, if the population standard deviation sigma is not known, then or if the population itself is not normally distributed, or if the sample size is not large enough, you cannot use the standard normal distribution. So when the population standard deviation is not known, you cannot use the normal distribution, you cannot use your inverse normal tables, and you cannot use your critical value ZC. Your critical values will not be Z-scores. Now, if the random variable in question is approximately normally distributed by the central limit theorem, you can use another distribution, which is very similar to the normal distribution, called the t-distribution. The t-distribution looks very similar to the normal distribution, although it does have some big differences. Now, the t-distribution does have its own table. I put a picture of the t-distribution table on Canvas under the Chapter 6 module. It is right below this section's PowerPoint, so it is right below the Section 6.2 PowerPoint, so you will be able to access it there. It is also available on Canvas under the Files tab underneath the Tables folder, and you can also access an electronic version on MyStatLab, and you can call up a picture of the t-distribution table on your homework problems for Section 6.2 in MyStatLab. So you don't have to memorize this formula because you won't really be using it that much yet. So let's say that if the distribution of a random variable x is approximately normal, then this is the AT score x bar minus mu divided by the standard deviation s over square root of n, and it's going to follow a t-distribution. Now this process is going to be very similar to what we did in the last section with your critical value ZC. Instead, this time your critical values of t are denoted by TC. And here are a bunch of important properties of the t-distribution, and you're going to notice that there are some similarities to the normal distribution. In the t-distribution, the mean, the median, and the mode are all equal and all equal to 0, just like the normal distribution. The t-distribution is L-shaped and symmetric about the mean. That should also sound familiar. The t-distribution is going to be bell-shaped-ish. The total area underneath the t-distribution is equal to 1. That's another important part. However, the difference with the t-distribution versus the normal distribution is that the tails are thicker than those in the standard normal. It is higher above the x-axis. And the standard deviation of the t-distribution is going to vary with the sample size. So this is another important property about the t-distribution that is different from the normal distribution, is that the normal distribution is just one single curve, whereas the t-distribution is actually a family of curves. So they're all going to be a family of curves of all different, they're all going to be very similar shape with that bell, they're going to be that bell shape, but they are going to be slightly different. And they're going to each be determined by this parameter called the degrees of freedom. So the degrees of freedom, which is most of the time abbreviated as DF, is the number of free choices left after a sample statistic such as x bar is calculated. Now, to find the degrees of freedom, that actually depends on the sample size. So if you're trying to estimate a population mean, then the degrees of freedom is going to be the sample size n minus 1, if you're trying to estimate a population mean, which is what we're doing in this section. Now, as the degrees of freedom increases, the t-distribution is going to get closer to the normal distribution. So the higher the sample size, the higher the degrees of freedom, the closer the t-distribution is going to look to the normal distribution. After 30 degrees of freedom, the t-distribution is very close to the standard normal distribution. So this is an example of the t-distribution being a family of curves. So for example, this graph right here has a degrees of freedom of 2, and you can see it's sort of bell-shaped, but look how far it is away from the horizontal axis. And as the degrees of freedom increase, so this graph here is a degrees of freedom of 5, you notice how it is getting closer to the horizontal axis, and it is getting closer to the standard normal curve. Now the t-distribution does have its own table, and in the next example I do have a picture of a little snippet of the t-distribution table so that I can show you guys how to use it, but you are going to be accessing the t-distribution table either on the Canvas module on that picture that I posted, or under the Files tab in the Tables folder, or on my StatLab using the links provided. So in the t-distribution table, each of the columns of the t-distribution are the most common tail areas, and these tail areas actually go with the most common levels of confidence. Now the rows of each of the tables are the degrees of freedom. Remember, to calculate degrees of freedom, you're going to take the sample size n, subtract 1. Now, if the degrees of freedom that you need is not in the table, you're going to use the closest degree of freedom in the table that is less than the one that you need. So for example, if you need a degrees of freedom of 57, degrees of freedom of 57, if you look at the table, is not there. So what you're going to use is you're going to use 50 degrees of freedom because that's the closest one that is less than what you actually need. So what we're going to do is we're going to find the critical value TC for a 95% confidence level when the sample size is equal to 15. So first of all, the sample size 15, that is n. We need to first find the degrees of freedom. So if 15 is your sample size, the degrees of freedom is going to be the sample size minus 1. So we're going to be looking at 14 degrees of freedom. Now in the body of the table, these are your critical values. So if you look at the top few rows, you'll notice this first top row right here, level of confidence. So each of these columns represents levels of confidence. So we've got an 80% confidence level, 90% confidence level, 95%, 98%, and 99%. So we're going to be looking specifically at a 95% confidence level, so we're going to be focusing on this column here, the 0.95. Now each of these rows stands for degrees of freedom. So we start with 1 degree of freedom, 2 degree of freedom, and etc. So the degrees of freedom that we are looking for is 14, so we are going to be looking at this row here, 14. So the body of the table will be the critical value TC. So we're going to go down to this row, degrees of freedom of 14, with this level of confidence 0.95, and when they meet in the middle, we get 2.145 right there. So right there, there is your critical value TC, which is 2.145. Now, unlike the critical values for the standard normal distribution, the critical value TC for the t-distribution is going to be different for each degree of freedom. So you're not going to be recycling critical values like you sort of could for the last section. You're going to have to look up each critical value individually for every single degree of freedom and every single level of confidence. Now, to construct a confidence interval for the t-distribution, this section we're going to be constructing an interval estimate for a population mean when we do not know the population standard deviation sigma. So when you're constructing a confidence interval for the mean, and sigma is not known. If sigma is not known, do not use the margin of error formula that involves sigma. So that margin of error formula that you found that we used in the last section involves sigma. If you don't know sigma, don't use the formula with sigma. If you're not given the population standard deviation, you are going to instead be given the sample standard deviation. So the overall process for constructing a confidence interval is going to be pretty much the same. You're going to use the same point estimate x bar, the sample mean, and you're going to be finding a margin of error e. However, the margin of error formula is slightly different for the population standard deviation not being known. So when sigma is not known, you're going to use this margin of error formula. So instead of the population standard deviation sigma, we have here the sample standard deviation s. And instead of using the critical value ZC, which is a z-score, we're going to be using the critical value TC, which is found in the t-distribution table. Over the square root of n here is exactly the same. So here is, in words, how to construct a confidence interval. Now remember, if sample standard deviation is not given to you, you can use a graphing calculator to find it, but for most of the problems that are going to be in this chapter, you will be given the sample mean and the sample standard deviation. Now, the first thing that you should check whenever you are asked to construct a confidence interval for a population mean is you need to first check to see if sigma is known or not known. So if sigma is not known, you are going to be using this process with this margin of error formula that involves the sample standard deviation. So you need the sample size n, the sample mean x bar, and the sample standard deviation s. Then, because sigma is not known, you're going to be using a t-distribution table. So if sigma is not known, you use the t-distribution. And you're going to identify the degrees of freedom, and you're going to find the critical value TC that goes with that level of confidence and that degree of freedom. Then you're going to plug in that critical value TC into the margin of error formula right there. Sample standard deviation goes in for S, and sample size goes in for N. Then once you get the margin of error, the process for actually building your interval estimate is the exact same as the last section. The population mean mu is going to go in the middle. The left endpoint of your interval, or the low end of your estimate, is going to be x bar minus e. And then the right endpoint, or the high end of your interval estimate, is going to be x bar plus e. So let me change color here, because the red is getting slightly annoying. There we go. So let's say that you randomly select 16 coffee shops and measure the temperature of the coffee sold at each of them. The sample mean, so the mean of this sample of 16 coffee shops, has a mean temperature of 162 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. So sample mean is equal to 162, that is x bar. And the sample standard deviation S, I'll write it in cursive because my handwriting is bad enough as it is. Sample standard deviation S is 10, and we selected 16 coffee shops, so our sample size N is equal to 16. We're going to construct a 95% confidence interval for the population mean temperature of the coffee sold. So 95% as a decimal is 0.95. We're going to assume that the temperatures are approximately normally distributed. All right, so since we know sample standard deviation and not population standard deviation, we need to use the t-distribution. T-distribution is used when sigma is not known. If sigma is known, you would use the normal distribution. Now, since we're going to use the t-distribution for this, we do need the degrees of freedom. So the degrees of freedom is 1 less than the sample size, gives us 15 degrees of freedom. So the next thing that we're going to do is we are going to find the critical value TC that goes with a 95% level of confidence with degrees of freedom of 15. So in the t-distribution table, you're going to go into the level of confidence 0.95 column with the 15 degrees of freedom row, and you should get a critical value TC of 2.131. So this is out of the T table, the t-distribution table. Now that you have found the critical value TC, we are going to find the margin of error. Now, because we do not know sigma, do not use the margin of error formula that involves sigma. We're going to be using the margin of error formula TC times S divided by the square root of N. So the margin of error is going to be that critical value TC that we just found, which is 2.131. times sample standard deviation S, which they gave us as 10, divided by the square root of the sample size N, so square root of 16. So then when you do 2.31 times 10 divided by square root of 16, you get a margin of error of approximately 5.3. Since everything else in this problem was rounded to 1 decimal place, I'm going to stay consistent and I'm going to round my margin of error to 1 decimal place. So then we're going to construct our confidence interval. Since this is an interval estimate for the population mean, I'm going to put population mean mu here in the center. The left endpoint is going to be x bar minus the margin of error e, And the right endpoint is going to be x bar plus the margin of error e. So we're going to take our sample mean, which was given to us as 162 degrees. We're going to subtract the margin of error, 5.3 degrees, and that will be the low end of our interval estimate. Then for the right endpoint, or the high end of our interval estimate, we're going to take the given sample mean, which was 162 degrees Fahrenheit, and we're going to add the margin of error, 5.3 degrees Fahrenheit. So your sample mean is going to be, your population mean is going to be between 156.7, and then on the right endpoint it is going to be 167.3. So your population mean is between 100 and, so here's what we are going to interpret this in context. With 95% confidence, we can say that the population mean temperature of all coffee sold at these coffee shops is between 156.7 degrees Fahrenheit and 167.3 degrees Fahrenheit. So then for this next one, let's say that you randomly select 36 cars of the same model that were sold at a car dealership, and you determine the number of days that each car sat on the dealership's lot before it was sold. So right away, this 36 cars, that is your sample size n. The sample mean is 9.75 days. So that means these 36 cars, on average, sat on the lot for about 9.75 days before they were sold. So that is the sample mean x bar. So x bar is equal to 9.75. With a sample standard deviation of 2.39 days. So it just gave us sample standard deviation, that is S. So S equals 2.39. We're going to construct a 99% confidence interval, so our level of confidence C is 0.99. For the population mean number of days that the model sits on the dealership's lot. So we are estimating population mean mu. So since we do not know sigma, the population standard deviation, we know the sample standard deviation S, we're going to be using the t-distribution. So for the t-distribution, we're going to need the degrees of freedom, which is 1 less than the sample size, so degrees of freedom is 35. Then we're going to use the t-distribution to look up the critical value Tc that goes with a level of confidence of 0.99 and a degrees of freedom of 35. So in the t-distribution table, you're going to look at the 0.99 level of confidence column, and the row of 35 degrees of freedom should give you a critical value of 2.724. Let's try that again. Tc equals 2.724. Much better. So now that we have our TC here, we're going to find our margin of error. So the margin of error formula, because we do not know sigma, we're going to use the margin of error formula, E equals TC times S divided by the square root of N. So then we're going to plug in the critical value TC that we just found, 2.724. Then we're going to multiply it by our given sample standard deviation, 2.39. over the square root of n, the square root of 36, gives us a margin of error of approximately 1.09. Since everything else in the problem was rounded to 2 decimal places, I'm going to stay consistent and round my margin of error to 2 decimal places. So now that we have our margin of error, we're going to construct our confidence interval. So I'm going to put mu in the center. For my left endpoint, I'm going to take the sample mean x bar and I'm going to subtract the margin of error e. Then for the right endpoint, I'm going to take my sample mean x bar and I'm going to add to it the margin of error e. So putting mu in the center, for the left endpoint, okay. All right, so for the left endpoint, we're going to take our sample mean, which was given as 9.75. We're going to subtract that margin of error that we just found, 1.09. Then for the right endpoint, we're going to take the given sample mean, 9.75, and we are going to add that margin of error, 1.09. So when we do all of the subtracting and the adding for our left endpoint, we get 8.66. And then for our right endpoint, we get 10.84. So for our interpretation, this means that with 99% confidence, we estimate that the population mean number of days that this model car sits on the dealership's lot is between 8.66 days and 10.84 days. So I will admit that when you are estimating population mean, it can get a little confusing, as to which margin of error formula do you use, which table do you use. And the answer to that question all depends on, is sigma known? Do you know the population standard deviation? That is why you should always look for that first. Because if, yes, you do know the population standard deviation sigma, then you are going to use the normal distribution with the standard normal table and the inverse standard normal table, and you are going to use the margin of error formula that involves ZC, the critical value z-score, and sigma. So if sigma is known, you're going to use the standard normal distribution and use the margin of error formula that uses sigma. Now, if sigma is not known, you're going to use the t-distribution with the sample standard deviation. So if you do not know sigma, you're going to use the margin of error formula that uses TC, the critical t value, and the sample standard deviation S, keeping in mind that you have n-1 degrees of freedom. We're not going to fully go through this example, but if you wish to for your own practice purposes, you are absolutely welcome to. So let's say that you randomly select 25 newly constructed houses. The sample mean construction cost is $181,000 and the population standard deviation is $28,000. Assuming that the construction costs are normally distributed, what we're going to figure out is, should you use the standard normal distribution or the t-distribution to construct a 95% confidence interval for the population mean construction cost? So for this question, we're just asked, what are you supposed to do? Which distribution should you use? And that all depends on whether sigma is known or not known. Remember, sigma is the population standard deviation, which it actually gives us right in the problem. The population standard deviation is $28,000. So sigma is known. Because sigma is known, we are going to be using the standard normal distribution with the margin of error formula that involves sigma. And because the population is normally distributed, we are going to use the normal distribution. Because we are using the normal distribution and we know the population standard deviation sigma, we're going to use the margin of error formula that involves sigma. So E is going to equal ZC times sigma over the square root of n. So that is basically it for section 6.2, because the process for actually constructing the confidence interval is the same. You're just using a different distribution to get a different critical value, and you're going to be using sample standard deviation instead of population standard deviation. Now, I will say, be very careful going forward for the rest of this chapter, because these first two sections we were all estimating the population mean. Starting in section 6.3, we are going to be estimating different population parameters. 6.3 is going to be estimating a population proportion. So anytime you're doing any of these confidence interval problems, make sure that you take 10 seconds to figure out which population parameter you are supposed to be estimating. Am I estimating population mean? Am I estimating proportion? Am I estimating Population standard deviation. What am I estimating? So just make sure that you are aware of what population parameter you are estimating before you go diving into a problem, because the process for margin of error and confidence intervals is going to be different for each population parameter that you estimate. So make sure that you complete section 6.2 before you move on to section 6.3. And when you are finished with that, I will see you all in the next video for estimating population proportions. So thank you all very much for watching, and if you have any questions, please feel free to email me, and I will see you in the next video.